Priyanka, you can start the welcome.
Dear past participants, thank you for your patience. Let's move on to the second session of the day. It gives me immense pleasure to introduce today's distinguished speaker for this FDP program session on AI pipeline and what the future holds. Although sir does not need any kind of introduction, we are very lucky to have Professor Dr. M.K. Datta with us today. Sir is currently working as Additional Pro Vice Chancellor, Amity University, Noida. He is also holding the post of Director, Amity Center for Artificial Intelligence. He is also visiting professor in BRNO University of Technology, Czech Republic. Sir is also included in the list of top 2% influential scientists published by Stanford University in the area of AI in 2023. Sir has supervised many PhD and MTech students in the area of AI. He was involved as the principal investigator for 10 funded research projects and has also filed 10 patents for his inventions. He has international cooperation with many scientists in many countries. Professor Datta has worked in many AI-related projects in the areas of healthcare, agriculture, food technology, marine sciences, etc. Sir has made many important contributions in the field of AI. The session will highlight what the future beholds for AI, including advancements in AI and growing role of AI. It will be informative, inspiring, and it will equip us with both conceptual clarity and practical knowledge. I humbly request Sir to take over the session and enlighten us. Please, Sir.
Welcome you, sir. Sir, your voice is not audible.
Okay, now am I audible?
Yes, sir.
Yes, sir.
Okay, so I'll share my screen. Okay, so thank you. So first of all, thank you all for inviting me in this important meeting, this important FDP. And I think it's quite late, and most likely everybody, because I'm in Delhi and it's quite cold here. So colleagues who are in North India, you must be feeling the cold climate. My name is M.K. Datta, and currently I'm working with Amity University in Noida. So prior to joining Amity University, I was working with a state government university. I was working with Dr. APJ Abdul Kalam Technical University, which is the State Technical University of Uttar Pradesh. So I was very lucky, there I had established the first AI lab of the state government in 2019. We started a program on MTech in AI. So my affection, my love with AI has been long. My papers, my research papers in AI, is dated back from 2009, 2010. So I have seen the journey of AI like the last 15 years, because AI has taken place after 2019. So in this presentation, what I'll do is that I'll run through a pipeline. I'll run through the basic machine learning model, maybe for the benefit of people who are not so expert, or for the beginners, for the medium range beginners. I'll run through a PPT where I'll start telling you like what is AI, and I'll try to go to the the most advanced models like MOEs and the language models, etc. So that will be the flow of my talk. So let's proceed. Okay. So this is where I start my talk. When I talk about a rule, let's say I talk about a rule. There's a traffic rule, or there is a rule where you can filter an email using a keyword. You may write a program. You can write a code. You can write a program, or you can make an automation on a robotic system, and accordingly from that, you can get your task solved. For example, if I ask you to differentiate between, write a code, write a program to differentiate between dogs and elephants. So what you do is that you take the weight of the animals as the x-axis, and you take the height as the y-axis. You plot the dogs, you plot the elephant. Then maybe there's a natural dividing boundary like a threshold. So if there's a new animal you bring in, if it is in the the other side of the downside of the boundary of the threshold, I say it's a dog. If it is, so there is no problem as such. It seems the problems can be solved very easily and very in a very easy manner. Now, what happens if all of a sudden I bring a problem like this? Let's say I give you 100 categories of butterfly, or 100 categories of fishes, or 100 categories of snakes, and I ask you to train a model to may write a code or an algorithm or a model by which you can differentiate these 100 categories, right? Now here comes the real problem. Or let's say handwritten digits from 0, 1, 2, 3, 4 up to 9, maybe more, or the problems where the complications is much more and there is more need of discrimination. Now the problem here, just a minute, I'll just come back. Okay, sorry. So here is the problem. Let's say I give you 100 categories of butterfly and I ask you, can you make a mathematical model to make a machine learning model, or sorry, a computer-based model? Most likely we cannot do it. So instead of writing the rules, let's try to, make some kind of arrangement where the machine starts learning from the data. And that is why, that is where the machine learning comes into picture. Or in other words, I'll say, make the machine intelligent. So this is where the machine learning is introduced. Okay, let's proceed. So rules versus learning once again. So how do humans learn this? Let's say recognition of a face, or speaking a language, or riding a bicycle, anything that you do. No one gives us a formula. We learn by experience. So if you look in a small boy who is learning to differentiate between different animals, or a small boy who is learning a language, it is completely experiential, and he learns. And the human system, for example, the nervous system, the auditory system, the visual system, everything gets trained automatically in solving different tasks. So can machines learn in the same way? Okay, from a baby to an experienced scientist, if you proceed, it's like, can I make an analogy? Like, if you have data and that's a trained model. So look into this analogy. Machine learning mimics how human learns from experience rather than explicit instruction, because there's a very beautiful very beautiful definition of machine learning, that machine learning is sort of a computer science where we do not teach the computer to explicitly program, right? We are dependent on extraction of pattern from the data and start learning. So this is a similar analogy where you can understand that lets the machine mimic the human system and becomes intelligent. Now let's talk about the evolution of AI. Initially we had hard-coded rules. Then comes the machine learning, like support vector machine, naive-based, random forest. This was in 2010. So we'll talk a little bit more about it. And then the shallow networks comes up. You start bringing the hidden. And then today in 2025, we are sitting on the transformer models where we are using Gen AI space. So this is the evolution, and this gives you a more understanding. I would like to have your attention on this. Now look into this. 1997. See, AI is not a very recent phenomenon. The mathematical models that is actually governing AI, for example, backpropagation, which is based on differential calculus, or stochastic gradient descent. Stochastic gradient descent is 1956, long back. Backpropagation is 1974. Now, this is the timeline of AI. So our 1990s and 2000 was machine learning, support vector machine, shallow networks like ANNs and random forest. Then comes 2000s, and then in 2000 we start the era of deep learning. So in deep learning we start with convolution neural nets, recurrent neural nets, and then LSTM models, GRUs. These are the models we started. And then in 2011, 12, 13, 14, all of a sudden, this deep learning becomes very popular. Then, we also have the transfer learning and like this AlexNet and all these things came up. The decisive year was 2018. So here I would like to have your attention. In 2018, there was a research paper came up from Google DeepMind. The name of the paper is, I'll show you a slide somewhere later. Attention is all you need. The attention mechanism, or the attention model, that is a transformer model, was proposed. And all of a sudden, after 2018, so 2009, 19, 20, 21, after 2018, you can see here, after 2018, whatever has come up, I call it as modern AI, because that's based on transformer. Now, if I explain this entire pipeline, I'll explain like this. Before 2018, AI was like a small insect, let's say a small ant. And after 2018, AI has become like an elephant. It has become like a dinosaur. So that is the powerful transformation of AI that happened with the transformer model that has come up in 2018. We'll talk a little bit more about it. But this is the flow of the AI timeline. And let me tell you, AI has become popular in 2000 after this transformer model. In GPT, T stands for transformer. There's a beautiful model, transformer model. So 2019 and 2020 were decisive years. I think OpenAI launched their first model in 2021, the first GPT, and the interest towards AI started. But please understand, AI existed long before, maybe 2 decades before, where, machine learning and shallow networks were working. Now, the difference between machine learning and process automation, I already mentioned. For a process automation, you can refine the rules and it can work accordingly like an assembly line technique. But for machine learning, the machine has to be intelligent enough to make decisions on its own. This is the basic block of a machine learning model. What you see here is that in traditional learning, you have a data and a program. For example, you want to find the square root of a number, or let's say you want to do a matrix multiplication, you have to write the code, give the input, you get the output. While in machine learning, it's little different. So what do? You do it in 2 steps. In the first step, you take data, train the model, and there is a trained model output, right? For example, you teach a machine to differentiate between cats and dogs, right? So you bring in a lot of images of cats and a lot of images of dogs, and you train the model. And when the machine is trained, when a trained model is called the optimized weights that we have, you take the trained model and give new unseen data. The model will be in a position to recognize or tell you the decisions which is expected to do so. And that is how the machine learning is explicitly split into 2 parts. The left-hand side, I call it the training model, and the right-hand side, I call it the test model. This is a basic fundamental difference between the traditional learning and machine learning. Now, let's say talk about low-risk decisions, where the mistakes do not matter. For example, I'm sorting the files by date, or I'm doing some, calculated arithmetic. So let's say the stakes are not very high. And where there are high-risk decisions, let's say the mistakes are very, expensive, like medical diagnostics, or let's say a fraud detection, or the Tesla autonomous driving, the errors can be very costly. It can cost life, or it can cost huge amount of finance. The systems must improve with experience. So these are some of the examples of machine learning model that we have done in our lab. So like, what we did, very interesting example. The first example is a cervical cancer detection. So what we did, normally in a country like India, pap smear is very costly. So and in fact, more than costly, it's like, it's not accessible. It's not accessible in the tier 2 and tier 3 cities. So what we started doing here, we trained a model. We got the data from, King George Medical University, Lucknow. I must acknowledge that hospital. So from there, we got the data. We trained a model. So what we did, for around 7,000 patients, we took their socioeconomic, features like age and the place of residence, and the social and the menstrual cycle. These are some socio-demographic habits, and also the histopathological parameters which comes through a blood test. And we trained a model, and now the app is deployed where a woman can actually punch in her socio-demographics and do the blood test and punch in the values of these blood values, the blood biomarkers, and it will return you a probability, a confidence score. What is the probability of that particular subject getting cervical cancer? So there's a full paper published on that, but this is just an example. I'm trying to show you how machine learning can be used in solving real problems. A couple of more problems. We worked on the Android malware detection. We extracted the feature in a tabular data, and then we could understand in a in a malware in an Android environment, which is a malware or not. A problem on robotics, where the next angle joint prediction was done. Also a glaucoma, let's say the cup to disc ratio or the neuroretinal rim, the ISNT rule. These are some of the features we use to train model using support vector machine, ANN. So these are some of the published work which we have. If anyone interested, I can tell you more about it. Then in the pipeline comes deep learning. Now, deep learning is a little bit different from machine learning. Okay, this is the father of the modern AI, Geoffrey Hinton. I think all of you know him. He was awarded Nobel Prize in 2024. He was the one who gave you the in fact, all the modern deep learning credit goes to him. Backpropagation and stochastic, most of the things he did it. So what I say here, a very beautiful quote: once your computer is pretending to be a neural net, you get it to be able to do a particular task by just showing it a whole lot of examples. So experiential learning, this is what it says. The difference between deep learning and machine learning is that you do not do the feature extraction manually. For example, in this particular picture, you can see in machine learning, there's an operator who is picking the features and then telling the model that these are the important features or the discriminatory features, and the model is trained. But in deep learning, the extraction of the feature is automatic. The features are extracted, which is inherently present in the data, and the model is trained. So please understand, in a deep learning, the amount of features that can be considered for training will be much more in comparison to machine learning. So machine learning always will suffer for some problems. Maybe the next slide you will see. Maybe this slide. Okay, this is a different slide. So here, what I'm trying to tell you a little bit about the deep learning is like this. This is the contextual understanding of deep learning. Actually, deep learning is, inspired by the human nervous system. So let's try to do an analogy. For example, I look into let's say I'm looking into some object and trying to understand the object, and how does it work. When I look into an object, the image of that object is from, for example, let's say I'm looking into a dog. The image of the dog is formed in my retina. There are some neurons which are being fired. Human body has got around 86 billion neurons. So a pattern of neurons will be fired when I'm looking into a dog. These neurons will get transmitted to the nervous system and reach a portion of my brain called as the visual cortex. Now in the visual cortex, already how does a dog look like, that pattern is stored, and hence I can, as a human being, I can identify or make an object detection like this is a dog or this is a cat. The same story, the same logic is mimicked in a deep neural network. So what you do in deep neural network is that, the patterns, for example, for a dog, how the pattern is to be activated. For example, any image that is fed to the, let's say the retina, you can see a dog or a cat image is fed to the retina. These images will be broken down into some data points, for example, pixel values, which is transmitted through some layers in a very similar manner of the human neuron system. Now, the interesting thing is that how the pattern is to be triggered. For example, in a human nervous system, the pattern of neurons that are being, for example, let's try to imagine, let's say you see have you ever imagined, if you see a cartoon, you start laughing, you feel happy. If you see a very sad image, let's say a dead body, you feel sad. Just understand the biological, significance. The pattern of emotion, the pattern that generates, the visual sensation in the visual cortex, and in return an emotion is activated. The same story we are trying to mimic in this deep learning models, where we try to optimize the weights and we try to ensure the pattern of weights which are being activated on triggering, for example, whatever input image we give. Let's say it's an emotional thing or an object detection or whatever. So the basic idea of this slide is that the deep learning model is very much mimicked from the human auditory system. A difference between the problems of machine learning that is actually countered by deep learning is something like this. For example, in the first picture you see occlusion, you see a boy reading a book, but if you use machine learning, you'll be defining the manual features, the handcrafted features, like there has to be 2 eyes, there has to be 1 nose, there has to be a jawline, and there has to be a lip contour, and then only it's a boy. Most likely all these features are missing. So a traditional machine learning will miss the features and may not be in a position to identify that a boy is reading a book. Okay, so that is the problem of occlusion, and this is actually overcome in deep learning. For example, there's a cluttered background, the animal is green and the background is also green. So what may happen is there is a possibility, if you pick statistical features or textural features in machine learning, there's a possibility that the object may not be identified. Intra-class diversity. Now you see so many categories of toys. For example, okay, let me try to give you an example. Let's say I take a simple example to classify between cats and dogs. Now there may be so many categories of dogs. In a white color spaniel dog, or a German Shepherd, or a Labrador, or maybe an Alsatian dog, or maybe a hound. So there are so many categories of dogs, and now when you are training a model, all these dogs belong to one class, that is dog. So inside the same class, there is so many different diversity. So how do you handle this diversity? For example, if you want to handle this diversity using a predefined features in a machine learning model, it may become very difficult. Okay, so these problems are actually overcome using deep learning model. Object deformation, scale variation, illumination intensity, viewing angles, that image deformity, the blurring, this is a motion blurring image. You see, these may fail in machine learning model where you predefine the features, but this may work very fine with your deep learning. So this is the deep learning history. 1952 was the stochastic gradient descent. The people who are teaching deep learning model, you must be knowing. You teach the stochastic gradient descent. It's a very important backbone for the backpropagation algorithm. 1958 you had the learning weights. 1974 you had backpropagation. 1986 you had the MLP, and 1998 you had the convolution neural network. My question is, if deep neural network mathematics and foundations were available 50 years back, 30 years back, 40 years back, why deep neural network, deep learning, and this Gen AI is popular so much at now? I'll try to answer this question in my next slide. So learning at scale. The world before the big data was pretty small. It was in some Excel sheets or some small databases. And all of a sudden, there was an explosion of data. Okay, image data, video, social media posts, sensor data, transducers data, and this huge data. It may be very difficult for the human being actually to analyze and manage this scale of complexity. So traditional algorithms work very fine when the data was limited or structured. But now when you have such a chaotic data, then you can imagine that the real data is highly nonlinear, highly complex. So we need AI models. We need AI models, and hence these AI models involved because the data outgrew the human analysis. The amount of data that we have, a human being, an expert, cannot analyze these data because human analysis have its own limitations. To answer this question, like 50 years back, we had, this one. We had the mathematical foundations like your backpropagation and your stochastic gradient descent. The question is why deep learning and generative AI right now? There are three primary fundamental reasons. Number one is the big data. Let's say you go 20 years back, you did not have storage. Am I audible to all of you?
Yes, sir, you are.
Okay. Okay, great. So there are primarily three reasons which are responsible for the deep learning resurgence and the generative AI. Number one is the big data. Remember, any generative AI model or deep learning models are data hungry. So currently we have got huge data space. So in comparison to 15 years back, what we had, or some 10 years back we have much storage possibility. So a lot of data we have, and we are in a position to train models because all these deep learning and Gen AI models are data hungry. Second is the hardware. This is important actually. Companies like NVIDIA has come up with technologies like CUDA, Computer Unified Distributed Architecture. So what we do here is that the computation has become hugely parallelizable. So let's say if you go 20 years back or 15 years back and you want to make a computer vision model to differentiate between some 10 different or 100 different animals, the training will go one by one. Let's say first it will train dogs, then it will train cats, then monkeys, donkeys, your elephants and tigers. It will go in a sequence. Today, with this CUDA technology, you can put even 500 classes, 500 labels of data, 500 different categories, each category having thousands and data points. The CUDA processors, the CUDA, I think you people are using the NVIDIA supercomputers. They're very much super capable of training the data. So this is another reason. And third is the software. That's a good news for the non-CSE background people. For example, my first PhD student, maybe some 10 years back, when she was working on an optimizer. She was working on an optimizer. Optimizer is making the learning rate adaptable in a deep neural network. So 10 years back she was working. So she had to write some 200 300 lines of codes. She had to write the differential equation, then she had to write the momentum equation, then she has to write all the code, maybe 300 lines codes, and then she used to see how this optimizer is behaving in making the training piece optimization. The good news for you people today is all the big players like Google and Microsoft, everybody has given you big libraries where those 300 lines of code has become a single line command. Today you have to just call Adam, ADAM, and just pass on the hyperparameters, and it will start working. So the good news for the non CSE, the non-computer background people is AI is almost becoming a plug and play model. The Keras library, I think all of you know Keras library, the TensorFlow model, the PyTorch model. They are built with so much strong libraries. Just you need to do a pip install, pick the libraries, and your task is done. You do not need to write the complex mathematical equation. For example, deep learning in itself is a very complex mathematics, right? You have to do the differential equation, you have to do the linear algebra, you have to calculate the distances every time and do it 100 times, 1,000 times, and you have to write the codes. And today you just you have Keras library, you have TensorFlow models, you have got PyTorch, and you're in a very good position of working with these models with single commands. So this is primarily the three reasons which are responsible for the resurgence of your deep learning. And so let's talk a little bit about convolution neural net. So what happened here is we started using convolution neural net, where we started using filter, making the convolution, and the receptive field, the weight sharing, the features. I think many of you must be knowing that CNN works on a window-based operation where the convolution is done, activation is done, pooling operations are done, and finally we go for a flattened layer and we make a probabilistic interpretation. So this is how the system is. Like, you do it again and again till the training accuracy is high, and the error becomes lower and lower. For better prediction, you do it. Now, the attention visualization. I'm talking about the history of this computer vision model. I have good interest in computer vision. So you see, when I'm putting a grid map, now this is interesting. The grid cam heat map is available. Now, what you have to understand here is that if you talk about the shallow networks from 10 years back when the attention was not available, the decisions were black box. Okay, we do not know. We say this is a dog or we say this is a cat, and the explainability was missing. So in the current times, AI has to be responsible and AI has to be explainable. Now, if you talk about a computer vision model, okay, the original image and the GradCam heat map image, you can generate this kind of images with Keras libraries and TensorFlow model. Now, this will give you some kind of an idea which are the features which are considered, adequately important or given more weights during the training of the model and identification and the detection of that particular object. So a bit of responsibility or a bit of, explainability is coming into picture. Next, we go to vision transformer. This is the computer vision pipeline. When I talk about vision transformer, we are using the transformer architecture. So we use a global, receptive field from layer 1, patch by patch we can proceed, split it into patches, and then the positional embeddings comes into picture. Now, this is the good thing about the, any transformer model is that you have a positional embedding, which adds to preserve the spatial information since attention is has a position information embedded in it, which otherwise is not available in your, the convolution neural nets. So one step ahead, you go in a vision transformer where you are preserving some spatial information also, which was not available in your the convolution neural nets, right? And also it has got a quadratic complexity. Now let's proceed. Now this is the attention visualization of your this vision transformer. Now for this vision transformer, if you look into the GradCam heat map, you see how this color code is being distributed. And it is giving you those pixels, the color codings are of those pixels that aggregate the attention across all the layers and has to show where the CLS tokens are almost, attends the most. So how much weight is to be given to which portion of the particular image is decided by the attention model, and hence attention is actually controlling by giving more weights to those portions, to those pixels which have got more discriminative power in making the decision. Let's talk about swing transformer. This is also interesting. So swing transformer works on patches. This is shifted windows for efficient hierarchical. For swing transformer, very popular in this one, your geospatial images, satellite images, because there we can break it down into patches. So here, once again, the interesting thing is that when you break this into patches, you are actually retaining the global information and the local attention also. So if you do it in terms of, here what we're trying to do is that we are shifting the window of the half size between the consecutive layers, enabling the cross window connections. And this, you will get big advantages where you are okay of doing the convolution operation in patches. For example, geospatial images or some block kind of an images where you don't mind making the operations block by block. Swing transformer is very popular and has got good attention, good attention in the current, times. So in swing transform attention, once again, you look into the feature activation map. The shifted window mechanism creates efficient local attention, and that progressively builds a global understanding. So when you are going, in that hierarchical mode in this swing transformer model, the attention, how it is built up, is having an explainability. Okay, so swing attention shows more structured and object-aware patterns, and the hierarchical design for captures fine details while maintaining the broader context awareness. So it is actually balancing between the global and the local context. So this is an architecture comparison. If I talk about CNN, the people who has got a vision interest, if you have got a vision in computer vision. So CNN, it has a receptive field is local, and from local to global it goes gradually. The complexity is linear. The inductive bias is translation equivalence, and it is good for limited data. If you have got edge devices, let's say you want to use an edge device like a Raspberry Pi, or let's say you want to use a Jetson Nano. So strong local features are used to train the model. VIT has got the receptive field is global layer from the layer one, from the first layer itself. The complexity is quadratic. So here you have a better, more complex problem. Inductive bias is minimal, more flexible, and it's good for large scale pre-training. Now, I mean, those of you who are in Hugging Face, you have seen that in the multimodal AI, the vision transformers are so much popular. Maybe we'll talk a little bit more about it. And swing transformer, is a window-based vision transformer where the global and the local, features are attention is adequately catered. And good thing is that the complexity is linear, and it works very good for images which has got patches like geospatial images. So future directions in computer vision, I think evolution of feature extraction that we have seen from VIT's global attention to swing transformers, your efficient hierarchical approach. Attention maps tells the story. So visualization reveals how each model sees. Right. Those color-coded heat maps gives you some kind of an idea where or which regions or which pixels more attention scores are being assigned. So CNN focuses locally and VIT sees globally. So this is an interesting update. So no one size fits all. Once again, you should understand that you have to choose based on the task requirement, the data that you have at hand, the data availability, computational budget. So even today, let me tell you the basic convolution neural nets and some of the standard convolution neural like nets like ResNet or VGG16 or VGG19, which came up around some 10 years, 15 years, maybe 10 years back. Still, they are very much in practice, where you can compromise with the fineness or the accuracy. For example, you want to make an animal detection system, or you want to put a CCTV camera in your gate, and you want to find if there is a person coming. So for them, you do not need that much computation power. Okay, so CNN models may be good enough for that. Some examples of deep learning experiments that we have been doing in our lab. All these are published paper. If you write my name and write this application, you'll get. For example, the leftmost is very interesting. We've developed a mobile app. We work with a research lab in Pune. There is a research lab of Pune. So Dr. Kaushik Banerjee is the director of that lab. He's a good friend of mine. So with them, we worked on a model where we used, computer vision models. We have to click a photograph of a fish. There are 3 discriminatory features: the eyes, the gills, and the skin. Gills are the respiratory organs of the fish. Now, if the fish is exposed to, another discrimination is 2 things. If the fish is exposed to, toxic substances like cypermethrin, which is a pesticide, or mercury, which is a, heavy metal, the fish becomes toxic for consumption. So we have trained models in our this mobile app, where we can take the photo of the fish, and one single click, the app will run, and we will tell you whether there are traces of mercury and cypermethrin, whether the fish is toxic or non-toxic. You can read on my name. Many research papers are also published with fish quality analysis, which we have been doing for the last maybe 7-8 years. Deep learning used in plant disease identification. We are very closely working with NIBCM. There's a lab in ICR lab in in Raipur, Chhattisgarh. So with them, we have a lot of data availability and connectivity. We have an MOU with them. So we are working with them. We are developing some mobile apps and also some computer vision models, which we have deployed in their drones, where early detection of bacterial infection and viral infection are being reported. Also, we have developed some apps, where the farmer can actually take a photograph of the plant parts like the leaf or the stem, and a computer vision model is mapped to a language model where recommendations are generated, which will help the farmer. We call it as I think I have named it as Kisan Mitra. So that is we have that actually. Third application I was trying to show you is mobile phone. So what in experiment we did, we exposed Drosophila is a very small insect. It's a very robust insect, genetically very similar to human beings. So we 8 hours per day, we dissected the brain and we used computer vision models to see if there was any deformation. We reported in our research papers that there was morphological changes at the cellular level of these brains, which actually indicates that long-term exposure of the mobile phone. So I recommend all of you not to keep the mobile phone very close to ear for a long time. Okay, and the fourth is also interesting. This is a DST funded project. I need to acknowledge DST. So there, what we did is that any carbohydrate food, if they are fried at very high temperatures, because in our country there's a problem. We reheat oils. Let us say you have a vegetable oil or a mustard oil. If you heat it for the first time, the temperature may go to 170 degrees centigrade. If you heat it for the second or the third or the fourth time, it becomes like a grease. It will reach 300 degrees centigrade. And if you fry carbohydrate food at those temperatures, there is a very toxic substance called as acrylamide that gets formed. We have used deep learning computer vision models where this is actually deployed in some of the research labs. So if you take a photograph of the image, you take an image of these carbohydrate fried foods, the AI model can predict and tell you if there is acrylamide content which is toxic for consumption or not. So you can see amazing applications. For people, many people, AI is GPT, Chat GPT. But please understand, it is much more. You can have your own customized solutions. These are the examples of computer vision which I have shown you. Let's proceed. Now we go to an interesting part. I call it as generative AI. Now, after 2018, the world has become a world of generative AI. The AI has shifted. Let's talk a little bit about generative AI. Now we are in the online mode, so I don't think we will be in a position to discuss much. There cannot be an interaction. Normally in my classroom, I ask, tell me which face is real, A, B, or C. So some people ask A, some people raise hands for A, some goes for B, and some goes for C. Right? This is the classroom situation. This is a real interaction situation. Then I tell, what if I tell you all these three faces are fake? None of these faces are real. So these are deep fakes. Let's talk a little bit more about it. Now you see, this is interesting. So what we are trying to do here is, there are some birds, okay? And in these birds, I've taken 4 features, okay? There are 4 features: shape, pose, texture, and background. Some has a water background, some has a sand background, even the textures and the pose and the shape. Now these are real images. The first 4 rows are real images. Okay. Now what I have done here is that if you look at the bottommost line, what I have done here is I have interchanged maybe the background or the texture or the pose or the shape. I have interchanged and I have generated some images. Now the interesting point is the features or the factors from different real images, if you have used to generate or synthesize a new image, the problem is, or the point is, the new image will also look as realistic as possible. Okay, let me try to give you an interesting example to explain the concept of generative AI. Now let's say we take some film stars, some models. Let's say I take Madhuri Dixit and let's say Aishwarya Rai and Deepika Padukone and maybe some more, and I make a database, a database, a latent vector database of all these faces. Now what I do, I'll run a code. I'll make a generative, a latent vector data, a latent space, and from that latent space, I'll start picking points. Effectively, what will happen? I'll generate a fake image. Those will have the eyes of Aishwarya Rai, the lip contour of, let's say, Deepika Padukone, the face or the jawline of some Madhuri Dixit. I'll pick the what do you say, the features, the low level and the mid level features of the face from real images, and generate a new image. Now please understand, because the low level and the mid level features have been actually picked from the real images, the fake image that I will generate will look very much real. So this is how actually a generative AI works. If you look into this GIF, the texture, the shape, the pose, and the background is changing, which is real. I'm changing it with some real, these backgrounds and some real, textures. So accordingly, the look and the feel of the generated image will be very much real. Have a look into this GIF. There's a video running, and this will give you a lot of idea how realistic data points are actually used to generate a fake image. But the point here is, what you have to note here, the low level and the mid level features used to generate the data or to generate the image, it has come from real data. Now you can imagine the same story. You can imagine Madhuri Dixit and your Aishwarya Rai and your this one Deepika Padukone and some more heroines. I have picked the eyes from a different, the lip contour, the smile, the face, everything I've picked from different subjects, and generated all of a sudden a new image. So what will happen is that the new image also will also look equally beautiful, equally pretty, very much ready for doing a modeling, or use that that fake face for a for some ad promotions. Okay, I think this GIF image has given you a complete idea how these images are being generated. So I think all of you have seen this, and this GIF is actually what do you say, an eye opener, or a very simple way to understand how generative AI works. Some examples of generative AI, this we call it a cycle GAN. The horses are being transferred into, transformed into zebras, or the zebras can be transformed into horses. We call it as cross-domain image translation. The technology that we use is called a cycle GANs. Now look into the source and the destination. What I'm trying to do is that if you look into the right hand side, generating realistic face images. Now if you see the low level and the mid level features, let's say the lip contour or the jaw lines, and some of the features of the source is maintained, and the destination is something like that, and just look into that, what kind of amalgamation of these features, or the mixture of these features, or interchange of these features is resulting into some kind of face images. And if you really see the small boy, or the girl or the woman in that image is actually retaining the low level and mid level features from the source from which we have started the AI training. This is called the deep fakes. Now, this is an interesting slide. I always show that. This is the concept of a latent variable. What is a latent variable? This photograph is taken from one of the Greek book. It's a Greek philosophy. Now, look into the prisoners. Let us say these prisoners as kids were brought here. They were born in a prison, and they have never seen what is a horse, or what is a dog, or what is an elephant. They have never seen. So they look into some shadows, okay, and they're trying to make out what these are. Okay, so they do not have concrete idea of the object, but from some kind of a shadow, they're trying to make their own assumptions and interpretations. Now, a latent variable works like that. Okay, in a latent variable, we dump in a lot of data, and we start assuming, what it can be, and we can make out. Let's proceed. This is a very interesting and a very simplistic understanding model of a generative AI called as GANs. We call it as generative adversarial networks. Now, what is this generative adversarial networks? Let us say there are two people fighting. You can see there are two boxers who are fighting with each other. In this particular case, there will be two deep neural networks who will be fighting with each other. Now, what are this? Let me tell you. Let us proceed with this. Generative, there is a deep neural network called as generator, and there is another deep neural network called as discriminator. And it's a two-game player. The generator is training itself to do a particular task, and the discriminator is training itself to do a particular task. Now let's proceed. Now there is a painter, okay, and this fellow is the discriminator, somebody who is actually trying to. It's a two-player game has started. Now the painter has drawn a random thing, and the discriminator fellow, this spy is checking whether it's a Mona Lisa or not. He says, no, this is not Mona Lisa. No, he's trying to draw a Mona Lisa. Now the generator goes back, retrains itself, and goes closer to Mona Lisa. Now the discriminator says, no, it is not Mona Lisa. It goes and retrains itself. It says it's Mona Lisa. This fellow says, no, it's not Mona Lisa. It still retrains itself now, and then the discriminator says, no, it's not Mona Lisa. And finally, one day, it has started from the random noise, and it is training and training and training, and it actually created Mona Lisa. Now, this is a two-player game. Okay, just try to imagine it like this. Okay, I'll give you a different example. One more example. Let us say that instead of painter, there is a person who makes fake currency. He is trained to make fake notes. And the discriminator is a person who is a bank cashier who is trained to differentiate between fake notes and real notes. Okay. Now what I would like to mention here is that every time the generator comes to the bank cashier and gives some fake notes, the bank cashier says this is fake. Now, now the generator goes back, the fake currency, maker goes back, he upgrades himself, he comes back, he states no. Now, if the training goes for maybe 50 times, 100 times, there will be a time where the discriminator actually cannot differentiate between a fake note and a real note, and it may pass a fake note. This may not be possible when two people are competing with each other, but this may be very much possible if there are two neural nets competing with each other. Please understand, two neural nets, okay, two neural networks, two AI models competing with each other. And this is a beautiful example of your generative adversarial networks. Okay, how does it work? You see, there is a generator. It takes the real images, okay, you lock the discriminator and you train the generator. Now, this is how the generator is being trained. You start with some random noise. You do a backpropagation algorithm. Backpropagation is the training of the model, and you start generating from the random noise. You keep moving, and you lock the this one, your generator, when you are training the discriminator, and then you lock your discriminator and you train your generator, and both of them are simultaneously getting trained. For example, one is getting trained to generate fake data, and the second fellow is the discriminator is getting trained to discriminate between the fake data and the real data. There may be a certain time where the generator has succeeded to generate a fake data which may look so realistic that the discriminator may pass it out, right? Pass it on and say, okay, this is a real data. Now, if you look into the generative AI timeline, this is another interesting model. So actually, it started in 2018 with the transformer model, okay, and from there, when the transformers come up in 2018, I think the GPT came up in 2021, the first GPT-1. Then 2022, you had Delhi, text-to-text transfer. Then you had Delhi by OpenAI. And then GPT-3 came up in 2023. 2024, you had GPT-4, and now you are in 26. We have GPT 5.2. So you see the speed with which they have come up. There's 70 billion parameter. GPT-4 is a 70 billion parameter model, which if it what effectively means, if you give a command to GPT, there will be 70 billion mathematical operation happening to return you, a output. Okay, let's proceed. Now, this is an interesting question. I always, when I show this, I think all of you have tried the nano banana, but I think Gemini has become very popular, where you give a command and you generate a image. But this, I made it long back. This PPT is some 2-year or 3-year old, where Gemini nano banana was not available. So I have generated this image using a stable diffusion model. The background, the base model in a nano banana, where you give a prompt and generate an image, is a stable diffusion model. Okay, so this is generated from an actual stable diffusion model. I did not use the nano because I generated this image maybe 2 years back, maybe 2.5 years back. Now, what I try to stress upon in this image is, I've given an image, make an image of a soccer player riding a tiger near a sea beach during sunset. Now, if you really try to understand the contextual meaning of this, one second. Now, if you really try to understand the contextual meaning of this text, and you want the text to generate an image, let's say I go to a human painter, I go to a human artist, and I ask the painter, can you please paint this image? Now, for the human painter, this may look like a very much, unreasonable, illogical, and a nonsense command, and most likely a human being cannot imagine it. A human being. See, human beings are driven by some creative imagination. Before he draws the image in a canvas, he has to imagine it in his, own senses, right? So human beings are driven by some creative imagination. Now, if we talk about AI, artificial intelligence, here I will make a very interesting comment. You know what? Artificial intelligence in itself is a wrong word. It's a misnomer. Anything that is artificial cannot be intelligent. Remember this. See, I am an AI scientist, so I'm telling this, that artificial intelligence in itself is a wrong word. Anything which is intelligent, it cannot be, anything that is artificial cannot be intelligent. So intelligence only lives with the human being. So the question is, if intelligence lives with the human being, how this command, how this prompt in a stable diffusion model has generated this image? Well, friends, this is done by doing some mathematical operations only. So a big LLM model like ChatGPT or Nano Banana or Gemini, they are not driven by some creative imagination or human emotions. So if you give a command, it doesn't anything, any human feeling. So 80 billion mathematical operations have taken place, okay? And this image has come in front of you. This is how a stable diffusion works. And this is actually a text to image. We'll talk a little bit more about it. Now, the same thing. Now, sorry, the previous one was text to image. Now we also have image to text. I think all of you these days you are doing it. But I made this long back, maybe 2 years back. I think I used GPT-4 to use this. So if I give you a text and I ask you to describe the text, it beautifully describes the text. So please understand the level of AI at which we are at the current times is great. The language model and the vision model, they are so much beautifully interconnected by some interconnecting trainable parameters that they are talking to each other, right? If I show an image, it can generate the text. If I give the text, it can generate the image. So there is a concept of multimodality coming into picture. Image can be converted into text, or the text can be converted into an image. We'll talk a little bit more about it. Cross-domain translation, this is, I think we can skip this. This is the GANs. So zebras to horses and horses to zebras, the cycle GAN. So if I give you an image of a place, how it looks in summer, using a generative AI, you can actually predict how it will look in winter, because generative AI has been trained to do that. Now, these are deep fakes. These are actually problematics. These are human face recognition. It has all the features that should essentially be there in human face. It looks so realistic just because, the low level and the mid level features of these faces are picked from real instances. Side view to frontal view generation. This is another interesting application of a Gen AI. Okay, now I come here. Let's talk a little bit about the mixture of experts. I think 6 months before, China was making a lot of noise. I think many of you have heard about the Chinese company DeepSeek. Now, DeepSeek was making a lot of noise, and it became a cause of concern for the big American companies like OpenAI and Meta. I think all of us remember maybe 1 year back, the share market of these big companies like OpenAI and NVIDIA, etc., had fallen some 10 to 12% in one single day, the day this Chinese DeepSeek was released. Now, what is this DeepSeek? Please understand, this is interesting actually. We call the concept of mixture of experts. So what is this mixture of experts? Now, for example, if you talk about the Llama 4, Llama 4 is a language model of this one, your Meta. Or let's say we talk about GPT-5 of this one, your OpenAI. Now, these language models essentially have got, let's say, 100 billion parameter models. Now, if I say 100 billion parameter model, effectively it means, if I give a prompt, let's say the prompt may be a mathematical calculation, or it may be a philosophical question, or it may be a reasoning question, or it may be a logical question, or anything. For any damn prompt, the model will, activate 100 billion parameters, and then output is generated. This is a big problem. If you really understand, the cost of computing associated with a 100 billion parameter model is infinite. You may not imagine. So much of compute is required, so much of cooling is required, so much of so many things are required, and the computation cost is extremely high. Now, China actually, I know Indian people who had proposed this, model in some research papers. I have a friend, his name is Shayak Mazumdar, and Shayak Mazumdar had written a paper on this long before China had actually, revealed this. But anyway, because the Chinese company DeepSeek had come up with this project, let me explain. So what we do here, if you see, if you understand the entire pipeline, look into this GIF that is working. So what we have done here, after the positional encoding, the layer normalization and the feed forward model, it goes through, and before in a transformer, after this decoder block, it goes through a softmax function, and it will actually give you a decision with a confidence score. But here what I have done, I have put it in the mixture of experts. There's the router. If you see, now this router will go, and depending on the task, let's say the prompt is a reasoning prompt, or the prompt is a mathematical prompt, or the prompt is a logical prompt. So we have divided the entire neural network into some sub. Have made subnets of 10 billion parameter each. 10 billion parameter for, let's say 1/10 is responsible for mathematics, 1/10 is responsible for logic, 1/10 is for reasoning, 1/10 is for some philosophy, 1/10 is for some general science, something like that. So that router will actually identify what is the class of the prompt, and accordingly it will go and activate that subnetwork which is responsible or which is trained to solve that particular task. So accordingly, what we are doing, we are saving a lot of resources. We are not activating all the 100 billion parameters which are available in this particular, this trained model, but using that router, the prompt, the first task will be, classify that prompt to which task it belongs, and accordingly it will go and activate that subnetwork to solve that task. Okay, now let us say there are 10 sublayers, okay, and 100 billion parameter is divided into 10 billion parameter each for this sublayer. So interestingly, for every prompt, if you can correctly classify it, the computing cost has come down to 1/10. So effectively, your cooling costs and all your logistics have come down by 1/10. So instead of making 10 subnets, if you make 120 subnets, your computing cost is coming down by 1/20. So imagine, so this is the trick. This is the innovation this Chinese company DeepSeek had given 1 year back, which was a big cause of concern for the big American companies like Meta and OpenAI, etc. But in fact, this is a very futuristic company, and now almost your Meta and all American companies and all the researchers are using even we are in our center, we are using this mixture of experts because we find this very interesting and a very efficient model where instead of activating the entire bunch of neurons, we are only activating those subnet of neurons which are responsible for solving the task. So we say every sublayer is an expert. So first sublayer is an expert of mathematics, second sublayer is an expert of reasoning, third sublayer is an expert of philosophy, something like that. So this is called as this architecture is called as a mixture of experts, and this is becoming very, very popular in the current times. And we in our center also, in our lab, we are using this very much in our research problems. So this is how the the mixture of expert works. So from the prompt, you run that layer. From the softmax functions, try to understand what is the task. Okay, let's say there are some 4 experts here. Expert 1 is mathematics, expert 2 is logic, expert 3 is reasoning, and expert 4 is let's say philosophy. So the softmax function output will go through a softmax. It will find out which is the particular task for that, and it will go and activate only that expert means that subneural network, and hence a lot of computational cost will be resources. So if you have got 10 subnetworks, your computation cost becomes 1/10. So almost DeepSeek, Meta, Microsoft, everybody is adopting this mixture of experts in the current time. Let me tell you, if you talk about the ethics, generative AI is really costing a lot of environmental pollution and environmental carbon footprints, because the amount of electricity or the amount of water required for cooling these servers is infinite. Actually, you cannot imagine how much is it. It's extremely high. So it is our responsibility to ensure and find algorithms and hardware systems so that less computation and less cooling is required. Otherwise, it will raise to your global warming, etc. Also, it's a threat actually. Okay, this is an example. So this is one of the project that we are doing. It's a geospatial project. So let's say I have put an image to the app, and I'm asking a question. Describe the image. Okay. Now, actually, what is happening through when I have put this image, the image encoder, the vision encoder will come into picture. The tokenization will happen, and it will go through. And when I say describe the image, okay, I've given a command. The text encoder, the text embedding will happen, and the tokenization of this text will happen, and it will go through. Now, in the router, it has to go and identify the task. Okay. So the expert 1 is, let us say, a scene descriptor. The expert 2 is an object identifier. The object 3 is, identify relation between objects. Maybe certain n number of experts I have. Now, when I have given the task, describe the image, accordingly, it has to actually identify which expert, which expert has to be triggered for this particular, this solution of this task. And accordingly, if you understand, in this particular task that has been given, one second, has been given, it's actually a scene descriptor, because I'm asking you to describe the image. So most probably the first expert, which will contain less number of neurons it will contain only a part of the neurons, part of the parameters that is available in comparison to the whole network. So as the above example requires image description, the scene descriptor expert is selected, and hence you can imagine, if I have 10 subneural networks, my computation cost has become 1/10. And this is a modern trend that has come up. And this is in a particular example I'm showing you. This is a project we are doing in our lab, actually, in our center. Okay, let's proceed. Now, RNN LSTM language model, we will talk about it. The difference between your convolution neural net and recurrent neural net is that, in recurrent neural net, the previous input also, the previous output also has got a relevance in generating the next output. Okay, for example, text. My name is MK Datta. I live in Delhi. So when I say I live in Delhi, I live in Delhi. So the words are not independent, but the previous word and the next words are interconnected. So what I do here is that if you look into this sequence, the inputs at that particular time step is also taken as an input, and there is a hidden step. There is an output coming from the previous time step, which is getting inside the particular neuron to generate the output. So there is a sort of a memory retention, or I say this is a memory, neural network which is working. Let's proceed. Now, RNN was successful in text processing, natural language processing, as all of you know. Then comes your LSTM. LSTM is little interesting, where there's a long and a short-term memory. If you can see the top rail, CN-1 to CN and H is the long memory context, and HN-1 to HN, if the bottom one is a short memory context, they're connected through some activation functions like sigma and tanh and so many things you can see. The maths is complicated, I'll not explain, but what we have done here is that the context memory has been increased in comparison to, because what we are essentially doing here is that we are selectively retaining the information that we need to transmit to the next stage. Okay, so there are essentially three parts. What is a forget gate, an input gate, and an output gate. So these gates are actually controlled using the sigma function and tanh functions, where we are very selective. It's like a conveyor belt running. Okay, you can pick and you can drop objects which you need and which you do not need. Okay, you can imagine it like that. So a long-term memory and a short-term memory is talking with each other continuously. It's talking to each other continuously. And interestingly is that it is retaining only those memory which may be required in the future context. Otherwise, which is not required, it will start eliminating them. If you talk about machine translation, you see, for example, in language to language translation, you talk about these days there are many multilingual chatbots, so this is important. Now, an encoder decoder architecture, if you see, if I use an RNN cell, where the output of the last RNN cell is going to the, that RNN cell, the diagram that I'm trying to show you. Let's say I want to translate an English sentence. How are you? Now the problem is the final hidden state of an encoder creates an information bottleneck. There are concepts like, vanishing gradient problem. So if you run through a long sequence of, cells, there may be a chance that there may be a vanishing gradient. Means, to explain you in a very simple language, gradients are the most important part which is responsible for updating the weights. And if the gradients vanish, the weights will not be updated. So that's an information bottleneck. And to solve that, the attention mechanism comes into picture. So the basic idea of it, this is very interesting actually, because the modern AI, if you really understand, the modern AI from that has come up after 2019 is based on this attention mechanism. So in this attention mechanism, what we are trying, for example, we want to translate this English sentence, how are you, to a Polish language. Okay. So what I do, the main idea here is generate a hidden state at each step rather than having a hidden step at the entire input sequence. But don't wait for the flow of the information from state 1 to the first state to the last state and then generate it. Rather, generate that hidden state and map it to the next level RNN cell. And here, what will happen here is that, because let's say state 1, state 2, state 3, state 4, four words, how are you and question mark. So these 4 states are being connected to the next level inputs for all the inputs. And then the next task is generating attention scores for all these inputs. Okay, this becomes a little bit more complex problem in mathematics, which we teach to our engineering students. But you can imagine, I mean, the participants can imagine here that an attention score will be assigned. This is, if you ask me, this is the biggest innovation in AI that happened in the last 10 years. Okay, the deep neural network came from Geoffrey Hinton 20 years back, and this was 2018. This paper came up from, Google DeepMind. The first author of this paper is Ashish Baswani. You can see there is another Indian author, Nikki Parmar. They are Indians, and this is the transformer model which was uploaded in archive in 2018. I think actually it was published in 2017 December, to be precise. And this has actually changed the world of AI. Now, if you really understand this architecture, if you see there's a positional encoding and this is basically encoder decoder structure. What essentially this has done is it has made the context memory of AI infinite, unlimited. For example, if you talk about an RNN model or a GRE model or an LSTM model, you can go back to some 20 steps or 30 steps of timestamps and retain information to generate the next output. Okay, this is what the research those days. Let's say you make an BiLSTM or you make a GRU, gated recurrent network units. So there you say that I have added 10 more steps. I can go, the retentivity of the memory was 10 steps more. And the research was like 10 steps, 20 steps, 30 steps, 40 steps. People were doing research and generating output. All of a sudden, this model comes up and it says it can retain infinite number of steps and generate output. The world changed that day. Today, all of us, we are sitting here, we are doing an FDP, we are doing seminars on AI. And trust me, friends, the entire business of AI has changed through this model, this architecture. And let us be very proud that the first author, Ashish Baswani, is an author from India, and Nikki Parmar is also from India. Nikki Parmar is from, I think, from BITS, and Ashish is from, I think Ashish Baswani is from BITS or somewhere, I can't recall. And Nikki is also, so, and this is that we'll talk a little bit more about this architecture. Now, if you see, let's talk about the language models. Now, large language models is, what is this larger language model of? If you say artificial intelligence, the bigger umbrella, then the machine learning, deep learning is a subset. And in the generative AI space, the large language model comes up. Now, this large language models is the buzzword, like your GPT-4 and DeepSeek and Llama 3. Now, how does it work? Now, this deep neural network for parsing and generating human-like texts. How do you do it? And Gen AI involved the use of this deep neural network to create new content, such as text, images of various forms. And now, transformer models, which has the capacity of infinite context memory, has the capability of generating new instances. It can be a new video, it can be a new image, it can be a new text, and hence we call them as generative AI. Now, what you need to understand here, the difference between the conventional AI that we had prior to 2018 was a task solving. AI was a task solver. Like, it will do a object detection, or it will do a segmentation, or it will do a classification, or it will do a regression. But the moment this Gen AI comes into picture, the difference is Gen AI can generate new instances, maybe image, maybe video. And currently you have seen the magic with your GPT-4 and GPT-5. It can write stories, it can write poems, whatnot. Okay, now let's a little bit proceed with our discussion with the pipeline. Now, GPT, the chat GPT first was actually trained over 300 billion words. Can you imagine how big is it? And can you imagine the computing cost of OpenAI? It's huge, actually. It's in millions and trillions of dollars are invested. Anyway, now these timelines. I think I'm coming close to the end of my talk. I'll move little faster. Modern era, GPT-1, GPT-2, GPT-3, GPT-4, BERT, your nano bananas, and
Sir, you have time.
your Gemini, everything has come up. the post transformer. And this is super exciting. Let's talk. Okay, I'll take another 15 minutes. Now, this is the paper. So any of you who are into computer science or you are in AI, I recommend you to read this paper, because the world of AI actually changed through this paper. Attention is all you need. Now, what is this attention? Now, if you look into this, I'll not go into the maths of this. There is a encoder and there is a decoder architecture, and you can replicate this and share weights to make an infinite context memory, architecture. Now, if you see, there are concepts like positional encoding, which is keeping a context of your position, and the multi-head attention comes into picture. I don't know how can I explain this. For example, if I say a line, I saw a boy using a telescope. Okay, listen. I saw a boy using a telescope. Now, if I say this, there are two meanings. One, I saw a boy using a telescope. I took the telescope in my hand and I saw the boy, right? And the second is, I saw a boy using a telescope. Means the boy was using a telescope. I saw a boy using a telescope. Please understand, both these sentences have got different contextual meanings. Okay, now let's say, okay, this is more complex. Let me take a simpler example. River bank and money bank. River bank is associated with river and water and sand. Money bank is associated with money. Now the word bank, when you make a tokenization of the word bank, the tokens are same. The tokenization of the bank in either case is same. The question is, how do you expect the machine to differentiate between a money bank and a river bank? At that particular stage, this multi-head attention comes into picture. Not sure. I mean, there is a good amount of mathematics associated with multi-head attention, but I'll skip that. But please understand, multi-head attention is such a powerful mechanism which can completely understand the contextual meaning of the information of the prompt that you are giving. Okay. Now here is the entire sequence I'm trying to run. The input text is to be translated. Let's say I'm giving an example. The input text is to be prepared for the encoder. The encoder access to the complete input text to be produced by the encoding for the decoder, and the encoder returns the embedding. Now you have the embeddings. I'll tell you a little bit more about the embeddings and the tokens in my next slides. Now this embeddings is fed to the decoder. This is the encoder-decoder structure, which actually this is the explanation. You have an encoder on the left-hand side. You have a decoder on the right-hand side. I'm trying to explain the functionality of this. Now when the embeddings are going to the decoder generates the translated text one by one. Okay, the pre-processing steps are: the input text is prepared for the decoder. A partial output text of the model completes the translation one by at a time. And finally, at the step 8, the complete output translation is being translated. Now, it's simple difference between BART. BART, I think all of you know, it's a Google model, and GPT is your OpenAI. Now, the difference is in your BART, it fills in the missing words to generate the original sentence. The logic is different. It receives inputs where the words are randomly masked during the training. Okay. And in GPT, it learns to generate one word at a time. And this is example. It receives incomplete text, but it can learn to generate one word at a time. So there is a difference. Actually, B stands for bidirectional. It looks into the left. It also looks into the right, both directions. I mean, it looks in the previous and the post, both the words, and it can generate a contextual meaning and accordingly generate the next level output. Now, what are LLM transformer? Why are LLMs transformative? Huge speed. It can process and analyze vast amount of text in seconds. You have seen. I think all of you are using your GPT-4 and Llama 3 and DeepSeek models. You can see the speed at which they are generating the reports. The scale, operate in multiple languages and multiple domains, and it is still scalable. You can build models on the top of models and add, sub-models to it. Intelligence. Its models have come here to stay with us, and it will be an integral part of our life forever. Now, AI assistants like Siri, Alexa, ChatGPT, these are everyday life usage. Content creation. I think many of you are using, AI for writing our emails, replies, our summarization of our documents, generation of reports. Even you can write poetries and songs. Customer support is using LLMs in a huge way, smarter chatbots and faster solutions. Now, a little bit more. I think I'll try to sum it up fast. Now, how these LLMs work? Let's say the input and the output relationship. Let's say the car is red. The next word prediction through this attention model. Let's say I tell a story, and the moment I give a prompt, tell a story, we start once upon a time, once upon a time. This is how the story has started. The bot is working. The question is how we actually do this. Let's do a little deeper, little and see. For example, I give a prompt, write a story. The positional encoding comes into picture, it comes into effect, and it tries to understand the positional encodings like write a story and find the contextual meaning of it. It passes through a sequence of layers. Okay, for me, for somebody like me, a GPT-4 or a Llama 3 or a DeepSeek is nothing but just a sequence of layers where there are trainable parameters and the mathematical operations happen. The tension and the feed forward, the tension, the feed forward, this, the feed forward models are happening, and it generates the confidence score. For example, what is the softmax output? What is the confidence score? So once, then there, in, when. So this is how it has been generated. And based on the softmax output, whatever is returned, you start writing it. So this is how, this is how your GPT is writing the story. Okay, the tokenization, please understand a little bit about the tokenization. What we do, we split an input into text of individual tokens, which are either words or special characters such as punctuation, characters, etc. Now, look into the right hand side diagram, the token embeddings which are available. Okay, what I do here is that I took an example. Let's say this is an example. So this is an example. First, we generate the token IDs. Token IDs are nothing but numbers. You can have many methods. There is one-hot encoding, bag of words. There are many tokenizers available in your Keras and your, in PyTorch, etc. You generate the token IDs, then generate the embeddings. After you have the token embeddings, like GPT-like decoder is GPT-like decoder, like only transformer. See, GPT-like decoder is only transformer, and in these token embeddings, when it goes through, this is being processed. Okay, now this is a more deeper understanding of the sequence. For example, let's say I use a text sample, or I take an audio sample, or I take a video sample, and how these embeddings are done. Okay, now you see these embedding vectors which have come up goes through. Let's say if it's a text, it will be a text embedding model. If it's an audio, it will be an audio embedding model, or if it's a video, it will be a video embedding model. So these deep learning models cannot process data formats like video, audio, text in the raw form. So we have to use some kind of embedding model to transform this raw data into a vector representation, okay, dense vector representation that deep learning architectures can easily understand and process. And this is how it looks like. And vector embeddings of different types of bird, for example, eagle or duck or goose, we can see this is how it is. The vector embeddings of the word squirrel will be somewhere else. Now we convert these token IDs into a continuous vector representation, okay, and so called the token embeddings, and we add the positional information, because unless and until you have the positional encodings, the contextual meaning or the semantic meaning of the sentence or the input will be lost. So this input embeddings, the positional embeddings, and this token embedding, the sequence you can see, positional encodings plus token embeddings. Token will give you the contextual meaning, and position encodings will ensure the context is retained in terms of position. For example, this is an example, or what is your name? I cannot afford to lose, what is your name? What name is your? I cannot afford to do that. So after the token embeddings and the positional encoding embeddings are fused, we get the input embeddings where GPT-like decoder, this only transform models can actually handle. No, this is how the more, more deeper sense how it is working. This is like the encoder 1, encoder 2, you can see. So what I do here is that machines will think in the attention models. It will try to generate the attention score. Actually, there's something called as a query matrix, value matrix, and a key metrics, query metrics, and a value metric. And based on that, some attention scores are generated. Now, once these attention scores are generated, we do self-attention models. And this self-attention model, when it's passed to the feed-forward model, we generate those, those embeddings which actually goes to the decoder. And this is how the entire work. So anyway, to summarize this, what I will try to tell you is that any language model with which we interact is nothing but essentially they're mathematical operations which operates on 80 billion parameter, 80 billion mathematical operations that it does to generate the outputs. So I think it is already close to 9 p.m. I'll skip these slides. So self-attention is like, how you generate the attention scores between the sequence of words that is available in a sentence. Now look into this. There is a key matrix and a query matrix. I'll not go into details. And this key matrix and query matrix will generate, the attention scores, the self-attention scores. Okay, and these value metrics which are generated from the word token embeddings and the hidden states from which it undergoes, and then it decides how the self-attentions are generated, which in turn works for your decoder. This is how the words are pulling words, like you see, please buy an apple or an orange. So the person has to understand or the model has to understand that apple is a fruit, and Apple unveiled a new phone. Here it has to understand that Apple is a company, a iPhone company, is a mobile company. So the contextual meaning has to be retained, and this contextual meaning has to be retained only with maintaining the sequence or the contextual embeddings. This is how, this is more detailed steps. I'll skip this slide. And finally, you go for that linear softmax layer where you generate the values, and these values, we'll call it as the attention scores, which is responsible for it. This is the entire pipeline of this this LLM training model. How do you build a LLM? Then you have a foundation model, and this foundation model you can use for performing certain tasks. The entire pipeline that I'm trying to summarize in this training model. The transformers. Now, in these transformers, what we normally do during the embeddings, we convert a text into a numerical vector that I've already mentioned, and this positional encoding to capture the order of the words, which is important, and self-attention layers highlight the relationship between these words, and in the feed-forward neural network, process the attention outputs into meaningful patterns. So this entire pipeline, which I've shown you in my previous slide, have been completely summarized, and the result is complex understanding of long range of dependencies. This is the final, what I can say, the summarization of the entire sequence of the pipeline, which I have mentioned. And actually, if you see, all these are trainable parameters. All these are trainable parameters, which will be trained as you train the model. I'll skip some of the slides. I want to give, we have some time, maybe 5 minutes more.
Sure, sir, sure.
I'll skip these slides because I'm running out of time. I want to discuss a little bit about the multimodal AI. Okay, I'm here. So here, what I try to do, I'll talk a little bit about the multimodal AI. So in a unimodal AI, what you do generally is you give one type of data to train a model. So the data may be a text data, you're training a language model. It may be images, you're training a vision model. Okay. But in multimodal, what you do, you are training a model with multi types of data. It may be text and it may be images. For example, I want a visual question. There is visual question answering are becoming very popular these days. We say VQA. I'm showing a image of a horse, and I'm asking a question. I'm asking a question. What is this? Or provide a picture of a horse, or write a song about it. So what I'm trying to do, or what I'll do, I'll put an image of a horse and I'll ask, what is this? So the text encoders, the text encoder has to make the tokenization and interpret what is the question, what is the text asked, and the vision encoder has to decode this. What is it? Is it a horse, or is it a donkey, or what is it, a monkey? And accordingly, both of them has to simultaneously work out to generate the result. Okay, so in this particular example, I have to describe the picture. Okay, so you see, I describe the picture means it has to understand my command of text and also read the image, and then it will say it's a horse. This is a horse. It is a brown horse, it is a black horse, something like that. Then as I provide a picture of a horse, so it is taking the text as an input and generating a image. So the stable diffusion model comes into picture. Write a song about a horse. Maybe you have to now think what is a horse and write a poetry on a horse. So generative AI model, which is trained now, let us say you have a model like your Gemini or your GPT-4 or your Nano Banana, where let's say talk about Gemini, Nano Banana, or GPT-4. GPT-4 is completely trained with image datasets. It is completely trained with texts. It is completely trained with both kind of data. Now, if you go to GPT-4 and say make the image of a horse, it can actually make the image of a horse, or you show an image of a horse, it will tell you it's a horse. Why? Because the AI model has completely understood the image as well as the texts. And these are not new things, friends. Let me tell you, these things have happened only after 2022. And this is still in the evolving phase. Okay. Now let's talk a little bit about multimodal AI. So examples are vision, images, videos, language, maybe speeches and text, audio, maybe sounds, voices, sensors, maybe radar signals, lidar, maybe it can be so many things. Now let's say we are doing a Chandrayaan. We are doing a project on Chandrayaan. We are associated with ISR also. For Chandrayaan, let's say you want to do a complete AI model. There will be images, text, there may be audio, there may be lidar signals, radar signals, and you need to combine everything to make summarization reports and conscious, decisions. How do you proceed with that? So each modality has to be captured with a different view of the world. Now, multimodal AI refers to machine learning models that are capable of processing and integrating information from multiple modalities or types of data. For example, I've taken this example and I'm asking you, let's say I put this photo to a GPT-4 or Nano Banana, and I say, give me a recipe for these cookies. Now try to understand the complexity of the problem. First thing is that the AI model has to understand what the image is. The image has to be completely decoded. Okay. The image, I mean, the vision model in your multimodal AI, like your GPT-4 or Nano Banana or Gemini, it will first, the vision model will come into picture. It will decode and it will understand these are some cookies. Okay. These are some chocolate cookies or something like that. Now, after it has decoded it as a chocolate cookies, it will go and search in its context memory if there is the recipe or the ingredients required to make these cookies. Now please understand the pipeline of or the sequence of event that will happen. The vision model, after it has recognized this as a cookies, it transmits this information to the language model. Okay, and the language model goes and search in its context memory if it has been trained with the ingredients how to make a cookies, and then from that context memory it will fetch that information and return it to you. Just imagine, it's a very complex process. You can try this. You can put a these days all of you are playing with this Nano Banana and your Gemini and this. So this is how it is working. So interestingly, for me, an AI scientist like me, the vision model is a trainable parameter. This your what do you say, this language model which is generated, the response is a language model which is a trainable parameter, and there will be an interconnect trainable parameter which is connecting the vision model with the language model. And once again, that is a trainable parameter. Let me try to relate it with a human being. For example, I go to a bakery chef. Okay, I go to a bakery chef and I show this image and I tell the bakery chef, can you please tell me what is the ingredients required and what is the recipe of these cookies? Now the process is the bakery chef will look into these cookies. He will realize that it is made of maida and some chocolates and something. Then the brain function will get activated, and then his mouth will start telling that this is a maida cookies and you will need some sugar and you will need some butter and you need some eggs to make this. Now if you make a synonymous or a relative synonymous model for an AI, the eyes of that person is a vision model. Okay, the text generation of the person is the tongue, the mouth, and the visual cortex, which is the interconnect between the language model between the mouth and the eyes, is another trainable parameter. So for me, the eyes is a trainable parameter, is a trainable model. The mouth is a trainable model, and the brain, which is the interconnect between my mouth and my eyes, is another trainable AI model. So if I can train these three AI models and interconnect them, I can get this job done. It is very similar how human beings work. Okay. This is multimodal data fusion. I think I don't have much time if I have something interesting. Okay, this is clip. This is interesting. So many of you maybe may have heard about this model clip. Clip is from OpenAI. This is a very, very popular model that has come up in Hugging Face. You can read more about it. It's a contrastive language image pre-trained model. It is available. It is trained on the source are the weights are open source, so you can use it for this. This is the tokenization model. If you look into this, there's a text encoder. Look on the right hand side. There's a text encoder which is responsible for generating the text tokens. There's an image encoder which is responsible for generating the image tokens. And you see how the image and the text tokens are being mixed in that particular matrix. And here the convolution will happen. So this is an interesting way how we have used the tokens from the image encoder as well as the text encoder, and the model is learning it simultaneously. For example, you show a red building photo and write this is a red building. So there is a red building photo and you write a text, this is a red building. Now the text encoder, this is a red building, and the photo, the image encoder of the building itself gets inside the AI model, helping the model to train its trainable parameters. Flamingo is also very popular. You can read more about it. Okay, I'll skip these slides. There are interesting applications of multimodal AI, like visual question answering, emotion. A lot of things are happening. For example, a mental health space. Let's talk about. We are working on a mental health project. Now, if you go to a mental health psychiatrist, he gives you a paper to fill some questionnaire. You fill the questionnaires. By the time the psychiatrist looks at your face, he looks at your hesitations, he looks at your body movements, he looks at your everything, and he then gives some kind of a recommendation like what is the situation. So AI models are used for that. Now for doing that, you will need a video analysis, you will need some text analysis. So many analyses will come up. Now friends, let me tell you, the generation of the time for unimodal data training has gone. Now unless and until you're in a position to go for multi data training model, you'll be outdated. So these are some examples. Maybe this is I don't think I have time. Agentic. Okay, let me quickly summarize what's it. Agentic AI. This is the latest buzzword, agentic AI. So what we do in agentic AI is agents. There are some agents. So these are essentially fine-tuned language models which are tuned for solving particular tasks. So to make a complete workflow automation, we actually integrate one agent with another. Agents are tuned LLMs, and the workflow is completed. For example, let's say I ask a question. I have $50,000 and should I invest in Tesla or should I invest in NVIDIA so that I get more returns? Okay, I give this problem to a fintech company. Now the fintech company has to do some experiment, some analysis. It will go to the Yahoo Finance and see what was the share market of NVIDIA for the last 1 year or so. For NVIDIA, it will do. For Tesla, it will do. Then it will go to some social media and see what is the sentiment, what is the positive sentiment or negative sentiment. So 3 or 4 tasks it has to do before it can come back with a specific recommendation. Now, for me, all these task solvers will be a fine-tuned LLM, a language model. Okay. And these language model will be integrated with one another. The one of the output of the language model will become the input of the next language model. And the complete task will be automated with minimum human intervention. Okay. So if you can do this, it essentially means the complete workflow is automated. And this is called as, this is called as an agentic AI. Agents are nothing but fine-tuned AI, which are tuned to solve a particular task. For example, in a fintech company or in any particular company, different AI models or language models will be trained for solving different tasks. They will be, connected with each other to make the complete work automation with minimal human intervention. And this has become, the latest buzzword. because agentic AIs are very powerful these days. AI can be used in arts. AI can be used in fashion. Okay, I'll stop my discussion. So thank you so much for your time. I think I'm sorry for overrunning my time. So most Indians may not know. I think this is my last slide. I'm sorry. Sorry. So most Indians are, may not know about this AI, but can't wait to find. I mean, I'm just end with saying that AI is the future, and uh, if many people ask me a question, I appear in many national television and many platforms. A common question people ask me is, do you think AI is going to take away my job? My simple answer to them is, AI will not take away your job, but somebody who knows AI may take away your job. So learn AI so that your job is secure, and and you do well. So thank you so much for your attention. Thank you so much for listening to me. Thank you all. If you have any questions, I can
Yes,
take.
sir. Sir Priyanka, please go ahead with the formal vote of thanks.
Thank you, sir. On behalf of organizing committee, I extend my sincere thanks to our esteemed speaker for sharing valuable insights, thought-provoking perspectives, and a clear vision of how artificial intelligence is shaping the future. Your expertise has truly inspired us to think beyond the present and prepare for what lies ahead. Once again, thank you, sir. We are truly honored by your time, your valuable guidance, and presence. Thank you, sir.
Thank you.
Thank you so much, sir. Sir, just wait 2 minutes for the photo. Thank you so much, sir.
Thank you, sir.